Hi, this is Kevin Emery with Quantum Easy. In this video, we're going to briefly discuss why it is that we need a bar chart or a histogram in order to plot the results of our quantum computer programs. In a regular computer system, you get this same thing out every time if you put the same thing in every time. They're reliable. They're deterministic. There's no random chance involved unless you have a random number generator, which even in that case has to base itself off of a timestamp or some other source of randomness from the external world. In the case of a quantum computer, randomness is baked into the very nature of how they work. You may have heard Einstein's famous quote, "God does not play dice with the universe." Well, his colleague Niels Bohr had a different opinion, and he felt that, in fact, random chance is baked into the fundamental structure of reality. The question went unanswered for many years until the Irish physicist John Bell had a mathematical insight that paved the way for us to actually measure whether or not random chance is fundamental in the world. And the overwhelming body of evidence shows that indeed randomness is fundamental to our world. Quantum computing takes advantage of that, and it provides great advantages for certain types of problems in math and engineering, perhaps artificial intelligence and other fields. But there's a disadvantage as well, which is that a single run of your quantum program, a single measurement of your quantum circuit, has no value by itself. It's only valuable when you run it a large number of times and then average out the results, because that's where the probability that underlies the behavior of the circuit comes to visibility. Without any further theory, let's take a quick look at a couple of the histograms that you see in the background here. So this is a histogram that's been posted on the Quantum Stack Exchange. You see across the bottom the labels of the various quantum states. We have a 4-qubit quantum circuit, and the results over some number of shots or measurements, something like 1,000 or 25,000. I don't know how many, because in this case it's only a graph of the probabilities. It gives a result of each of these outcomes some percentage of the time. We can see that there's an overwhelming weight on this answer, so you could think of that as the right answer, or at least it's meaningful. Whereas if you were to run it only a single time, we don't know that it comes out 0010. A single run might have it come out 1000, which is a quote-unquote wrong answer that's unlikely when you aggregate the results over a large number of runs. Similarly, the measurement results from our Bell circuit that we've been building in some of the other videos comes out to either 00 or 11 when measured after the entanglement part of the circuit has finished. And it never comes out as 01 or 10 unless there's an error involved in a real quantum circuit. We see a 50-50 distribution where we have approximately 16,000 double zeros and 16,000 double ones. Now this was run a large number of times, but if we run it a smaller number of times, like say 12, then we're going to see a little bit more variation between the double zero and the double one results, and it won't look as flat. So it's kind of like zooming a lens in. The larger this number of shots is that you pass into your simulator or your actual quantum computer transpile function, then the more accurate your results are going to be. With only a small number of runs like this, you can see big differences between the states. And a single run is essentially meaningless. So that's why we need these histogram plots and a large number of executions to get meaningful results from a quantum computer, where we have systems that are fundamentally probabilistic in nature.